for n cut for S is going to be the cut is only going to cut one edge here. It can be 1 plus 1. And the volume of the left side will be 1, 2, 3, 4, 5, 6. So 6 here. And the volume on the right side is 1, 2, 3, 4, 5. Okay, so 1/6 plus 1/5. And according to my notes, this is 0.367. And then the normalized cut of the blue one, so n cut S prime, is going to be 1 over 1 plus 1 over 10. Okay, so that, and this is going to be roughly, I think that's, which is 1.1, right? So the normalized cut of S is much smaller, right? And this is what tells us it's the right cut. And if you can check all other ways of doing it, this is going to be the best way to do it, like I showed you. Okay, so this normalized cut is a pretty good measure of telling us how to split it, so we keep it roughly balanced. So we aren't just cutting off these singletons, and also it doesn't cut too many edges. Okay. Good. Okay, so now the question is, how do I find this best normalized cut? How do I do it? It seems, and if you've taken an algorithms class, you might be thinking maybe something magical with flows. It turns out that that's not quite the right solution here. The flows will give you just the cut, but not the normalized cut. Okay, I'm going to try and transfer him into the stroller. Let's see what happens. Can you help me see if you can lay that flat to take this off here? Just push it out. And then see if you can lay that flat. There's something in the back. You need to release the drawstring. Yeah. All right, while you are thinking about how to solve this problem, we'll take a little bit of a, no, there's, okay. Well, no, we've got an expert coming, it looks like. Great. Okay, let's see if this works. Here we go, bud. Okay, you want to sit here and watch? There you go. Okay. You want to watch a show? You want to watch your show? You want me to hold you more? Okay. Okay. He just doesn't want to sleep through the rest of the lecture. He won't ever know how to solve for the normalized cut. Okay. Now that you've all been waiting in anticipation, so how do we do it? We do it through what's called the magic of what's called Laplacian, Laplacian matrices. Okay, so there are two ways of. You want water? Okay. There are two ways of defining the Laplacian, and the other water. Okay. There are two ways of defining the Laplacian, and so the one I'm going to explain first is a little bit easier to explain. I'll call this the unnormalized Laplacian. There's different names in the literature, but it doesn't quite optimize the normalized cut. And then I'll tell you something I'll call the Laplacian, which does correspond with optimizing the normalized cut. They're both useful. The normalized one, which I'll just call the Laplacian, will work a little bit better and corresponds with the normalized cut. Okay, but we'll start with just the unnormalized Laplacian matrix, or maybe I call this, yeah, good. So this will just be the unnormalized Laplacian matrix. And so I'll start with this graph, and then its matrix representation. Right, so this is also known as just the adjacency matrix of the graph. So the 1 tells me if A and B are next to each other. Now I've taken away the labels on the columns. I'm just thinking of this as a matrix, a n by n matrix if there are n vertices here. And so I also create another matrix called the diagonal matrix. Right, and this is simple because it only has non-zeros on the diagonal. Right, so everything is 0 except for on the diagonal. And what's on the diagonal is going to be just the degree. I guess this is sometimes called the degree matrix. Yeah. Excuse my writing. Okay, at least today I have an excuse for my poor handwriting. So other days I guess I don't have an excuse, but today I do. So so this is you can also just call this the degree matrix, because for the column corresponding with A, the 3 is how many edges are adjacent to A. Right, so I can look at actually the capital A matrix and I can just add up that column. And so the degree has the property that if I add up that column or that row, then it's that sum. That's exactly the number there. You can check that for all the columns up here. Okay? So I've got these two matrices, the adjacency and the degree matrix. And so then the unnormalized Laplacian is just D minus A. I just do a matrix subtraction that's element-wise subtraction. Right? And so I have I have the diagonals I have the degrees on the diagonals, and then I have negative ones wherever there's an adjacency. And so in this graph, I could have had some self-loops where I have an edge to itself. I'm just going to ignore those in this case. And you can just pretend those don't exist, and that probably works fine in this case. Otherwise, you'd have to do maybe something weird with those on the diagonal to make sure these numbers made sense. But you can just ignore an edge back to the same vertex. Okay? So this is the unnormalized Laplacian. And this is kind of a simple version. Kind of, if you look at any row or any column and you sum up the values, it's going to add up to 0. Right? Because the degree was the sum of all the other ones, but I made those all minuses. Right? So you can think of kind of water flowing into a node that tells you at its degree I have 3 pipes going in, and I have 3 negative going out. Think of it describing the flow, and when we talk about directed graphs, we'll think about this flow kind of a bit more later in the semester. Okay, so this is the unnormalized Laplacian. It's pretty simple and straightforward. Okay, but in order to use this, right, so in order to understand this, we kind of want to figure out how to split, and by itself this doesn't tell us how to do it. What we are going to need is the Eigen decomposition of L0. Okay, so switch it over here. All right. Okay, so we're going to need the Eigen vectors and values of L0. Okay, so who's heard of the Eigen decomposition of a matrix before? Okay, and who hasn't? Okay, a few. Okay, so we'll talk a bit more about what this is when we are in the PCA part of class and how to think about this a little bit more. We'll see some intuition today, but what an Eigen vector is kind of given a square matrix. An Eigen vector is so let's see, V is an Eigen vector of M, which is a square matrix, so we'll say n by n. If mv equals lambda v, where lambda is a scalar, and then this is called the eigenvalue. Okay, so what's happening is I can multiply the matrix by a vector, and I get back essentially the same vector up to a scale factor. Okay? Now, this is not a normal thing, right? Usually when you multiply, like it has to be a square matrix so it has the right dimensions of the vector, and usually you get back a totally different vector, right? That's the whole point of the matrix, is to get back a different vector, but there are these very special vectors where you essentially, you get back that vector itself. And these are called the Eigen Vectors of M. Okay, so if M is full rank, and it's also M is also positive definite, and I believe all matrices formed this way will be positive definite. I'm pretty sure about that. I don't. I'm like 98% sure about that. So then you're going to have exactly n eigenvectors and eigenvalues. Okay, so these are going to come in pairs, right? You're going to have like you're going to have vi and lambda I, and I'm going to get this kind of these n pairs of eigenvectors and eigenvalues, and this is going to give me kind of it's going to turn out that this is going to form a basis of the matrix M, and we'll talk a bit more about this formally later on in the semester. But for now, just know that there's this operation you can run inside of MATLAB or a matrix like in NumPy inside of Python, and you can get these eigenvectors and eigenvalues. Okay? So let's look at what these are. Okay, so these are, for this unnormalized, the unnormalized Laplacian of this graph up here, I'm going to get these eigenvectors and eigenvalues, and they're typically going to be sorted by, they're going to come to you, when you call this, sorted by the eigenvalues. So this will be lambda 1, this will be lambda 2, lambda 3, and so forth. And this vector here is v1, v2, v3, and so on. Okay, so I'm going to run this in MATLAB. It's just eigs of L0, and it will just give you these as the outputs, right? So you can just think of running this as some black box operation. And so let's look at this just a little bit here. The first eigenvalue in vector, this one here, is not that useful. It's always going to have an eigenvalue of 0, and it's always going to have all of its eigenvector is always going to be 1 over square root n, where I have n different points. And it's going to be true for any sort of graph. And what this basically says is that there's one connected component of the graph. That's kind of what it's telling you. That if I have two connected components, that means that the graph is not connected. I cannot walk along the edges from one part to the other. Then I'm going to get two vectors like this. Okay, so that's really not telling me anything interesting for clustering, other than, I mean, if I have two vectors, then I said, well, the first way to split it is to cut it where there are no edges, right? But that's kind of not interesting. That's not the interesting case. The second one is the interesting one. This is called the Fiedler Vector, and this comes up in a lot of different analysis. And so this one is going to tell us something really interesting about this graph. Okay, the eigenvalue is going to tell us kind of how important it is, roughly at the rate of, the importance is roughly 1 over square root I. Okay, so the smaller it is, the more important it is. Okay? And so this one is the smallest non-zero one, and this is the most important. Right? And so the lambda 3 is over 1, right? So this is much bigger. Okay, so this is much less important. Okay, but the eigenvector is going to tell us something interesting here. The eigenvector basically tells us a 1D representation of this graph. Okay, so it's telling us if I were to put this graph onto the line, map it onto the line, what's the best way to do so? Okay? What's the best way to do that? And I'm not going to specifically define best right now. It's going to kind of have to do with the normalized cut. When we talk about PCA, there's going to be a much more clear definition of best. So when we get to that, you can come back and think here and kind of understand it's something like that. I'm not going to kind of quite go through that. This will correspond with some different cut metric for the unnormalized Laplacian matrix. Okay? Okay, so how does this work? So how can I use this to project the graph down to one dimension? How would that make sense to do? Yep.
Maybe the values that are closer, like Euclidean distance in the 1D are closer in the graph.
Yeah, right. That's basically, you can do something even more specific than that.
I was thinking like pick the two furthest points, place them, and then work around them.
Well, so I mean, there's something even simpler. So I'm going to get this vector is of length n, where I have n vertices in the graph. Each entry actually corresponds with one of the vectors, right? So this corresponds. This is the row that corresponds with A, B, C, D, E, F, G, H. Okay, so this is the entry associated with A, minus 0.36. B is minus 0.42. If you look at D down here again, it's also minus 0.36. Okay, what I've done here is I've drawn it using the first, I've created an embedding of this graph into two dimensions using the first two eigenvectors here. So I've just taken the first two eigenvectors, and if I just look at the first eigenvector, just the x-axis, then I've taken, B, let's look at B here, minus 0.42, that's the x value of B. Right, its y value is 0.18, and that tells me how much above the axis is here. Okay, so I've done this, I've put it down into 1D. I've actually used the first two to put it into two dimensions. Okay, so we can use two dimensions, but we really only want to use we can get away with only the first dimension here. I just happen to have drawn it in two dimensions as well, which you can do 2 or 3 or 4 dimensions using the first 2, 3, or 4 of these eigenvectors. Yeah.
What was yi?
What?
Yi. Yi. This is 1 over the square root of yi.
Should be lambda I.
Oh.
Those are.
What is that?
Lambda is the Greek letter. That's the eigenvalue, right? So the eigenvalue is here, right? So this is the eigenvalue. So I'm going to run this function inside MATLAB, and it's going to give me all the eigenvectors and eigenvalues. So these below this black line here are the eigenvectors, and the value above it is the eigenvalue. So that tells me how important it is, right? The importance is, I scale this way. Right, so I can do this, and this is, so what I've actually drawn as the location of B is actually going to be V1B times 1 over square root lambda 1. Here you go, bud. Okay. All right. Switch arms here. Okay, so I've actually drawn that for the first coordinate. I've scaled it by the importance, right? So what it does is it allows me to stretch it out a little bit further in the dimension, which is more important. Otherwise, they'd be scrunched up. Otherwise, these eigenvectors are normalized, So they're set so the sum of the squares is, the sum of the squares of the values is equal to 1. So if I took the eigenvector and I squared all the values, I would add it up, it would add up to 1. Right, so then the eigenvalue then tells me how to scale these afterwards. Okay? So then once I have them in this one-dimensional setting, in order to do this cut, right, all I have to do is, sorry for the left-handed line here, but I just draw them, I split them at 0. The ones less than 0 are in one half of the cut, the ones right on the right side 0 are on the other half of the cut. Yeah?
So why do you have two connections at E, I think?
Yeah, so A and D, right, you're thinking about what's going on right here. A and D are exactly on top of each other, right? They have the exact same coordinates. They're both minus 0.36 and 0.08. That's the same for A and D.
Yeah, but that's not exactly what I was looking at. The triangle over there? Do you see the triangle?
Yep.
Yeah, so why do you have the connection with that?
Yeah, so this is the same graph as up there, right? The graph did not have any geometric meaning to it. It just has vertices and edges, right? So the coordinates of those points actually didn't matter. I didn't want to use those coordinates. I'm just given it. Remember, the input is just described mathematically as a set of vertices and a set of edges. So I don't have this embedding. This tells me how to draw the embedding, right? So that it makes sense in terms of these cuts, right? And so it's the exact same graph. You can't see the rest of it here because A and D have the same coordinates. Okay. Let's bring you to another question. Why do A and D have the same coordinates? Or over here.
Is that because they are the same distance from every other point in the graph?
Yeah, from a perspective of the
Like,
graph,
relative to each other.
they look exactly the same. They're all connected to B and C and each other. So from the perspective of the graph, I can't tell the difference between them. So it makes sense that they would have the same coordinates here. If I go back here, eventually they differ. The last eigenvector has one of them, like has everything zeros except those two, and it arbitrarily decides to make one of them positive 1 over square root of 2, one of them negative square root of 2. For the vectors, eigenvectors, it turns out the sign of that doesn't matter. I can multiply everything by -1. It essentially has the same meaning, right? So this basically just arbitrarily splits those two coordinates. But there wasn't really a better or worse way. Okay, so those are exactly the same because in the graph they look the exact same. Yeah.
So you said that we're going to split the graph at 0. Does that mean it's possible on one side of 0 you can have more nodes than on the other side?
Yeah, right. So the simplest way is just to split at 0. In practice, you can do a little bit better by saying, well, I'm given a sorted order, and I'm going to sweep that sorted order, and I'm going to consider only those cuts based on the sorted one-dimensional order. And I might say that C is slightly across the line, and it's better to cut here. So I can compute the normalized cut score and see whichever cut gives me the best thing. So I could have considered putting C across. Sometimes you get so that there's a big gap. There's a couple things that cross just over the origin, and then there's a really big gap before you get to the next one. And in that case, usually it's better to cut in the big gap when you draw them. Or it can be, these things could be hundreds of thousands of nodes, and you can't really see it if you plot them. You just have to kind of trust the algorithm. You put them to one dimension and you scan left to right, and you just check the normalized cut score for all of them. Right? It takes constant time to update the normalized cut score as you sweep across, so this doesn't really cost you that much extra. Yep.
What kind of values would the V going into the eigenvector?
Is what going?
The V, if you go back one slide.
Yep.
V lambda, or maybe one more, lambda, V lambda VI. What kind of values is VI going to be?
Right, so VI is going to be an n-dimensional vector. Yeah, so Vi is an n-dimensional vector, because I have to multiply it by an n matrix M, and only an n-dimensional vector is a legal operation. It could be a matrix, I guess, but it's a vector in this case, and I get back the vector. Right? It's on both sides, but it's scaled by some amount, and that scaling is lambda. Right. And when we talk about PCA later on, the larger values are going to be more meaningful. And these larger values are basically going to correspond with 1 over square root lambda in those cases. All right. Okay. Okay. Yep.
What do the distances mean between points?
It's just kind of an embedding. There's probably some good meaning. I can't tell it to you offhand. There's probably something useful that you can get out of about it. There's some good explanation. I don't have this offhand. It tells you that there's some rationale for it, and I think it's even actually there's a clear explanation for the normalized Laplacian, which we'll talk about next. It corresponds with some, I think, like there's some way of measuring some form of distance between all the vertices, like a metric distance, and this is kind of the best low-dimensional approximation of that. There's some way to kind of recover that sort of property, but I don't remember the exact statement of it right now. Yeah.
So right now we're just representing the graph in like 2 dimensions, but we can just keep using.
Yeah, you could keep using higher. Now it turns out for the algorithm we only need 1 dimension. You could do something where you said, I'm going to split it 4 ways, right, at once, right? So I'm going to embed the first 2 dimensions, and each quadrant is going to be one of the 4-way splits. And this turns out this is roughly the best way to do it. I'm going to have E, F, and G in one cut, H in one cut, C in one cut, and A, B, D in the other cut. Right? That's about the best 4-way split you can do. And that corresponds with the 4 quadrants here. It won't always be the perfect thing for 4-way cuts, but you could do that if you wanted to. Yeah.
So if you want more than one cut, would the strategy then be to just calculate this Laplacian matrix one time and then go down the importance?
You could do that. So that's a little bit faster way to do it. Kind of the real optimal way is then to say, once I have a cut, I have a new submatrix, a subgraph, and I'm going to rerun the whole algorithm in the subgraph. Yeah. They're either, I've seen people do both of these. So, yep.
Does the cycle mean anything here?
No, there are no cycles are not important here. Well, when we talk about directed graphs, the cycles will be important, and we'll come back to that. That'll be in the last section of the class. We'll talk much more about these sort of issues. Yeah. Okay, great. Let's talk about the Laplacian matrix now. So this unnormalized Laplacian was a bit easier to work with. It's kind of fairly intuitive how to define it. This one's not that unintuitive. It just requires this d to the minus 1/2 matrix, where you're like, okay, a matrix to a negative fractional power, what does that mean? Well, it's because this is a diagonal matrix, it only has entries on the diagonal. I'm just taking each entry on the diagonal to the negative 1/2. Right? So I took this degree matrix and I took each entry on the diagonal to the negative 1/2. Okay? So then I create the normalized Laplacian instead as I, the identity matrix, minus this d to the minus 1/2 times a times d to the minus 1/2. Okay, so it's a bit more complicated, but what it has is the diagonal is now all 1s, and this one is and it's going to be symmetric and has zeros in the same spots as before. Okay, so it turns out this is a different way. It's called normalized because you can think of taking the old one, which is I minus or d minus a, And I'm basically normalizing by multiplying through by this d to the minus 1/2 matrix. Yeah. We made it through most of the lecture, Max, okay? All right. Okay. So just don't worry too much, but this one is a bit more optimized for the normalized cut score we talked about. And then we do this the same way with the eigenvectors of this one. They're a little bit different now. The first eigenvector does not have quite the same properties as before. The first eigenvalue is still 0 because there's one connected component. And the second one will still be 0 if there's only if there are two connected components and so forth. And it's the second one here that matters the most again. And so I took it and I can embed this one into 2D, and it looks a little bit different here. But you know, I flipped the axes again. The axes, if I flip them, the negative sign doesn't matter, so that's not a big deal. But the cut's a little different. You know, if I look at the second one, it has F below on the same side as H where I didn't before. And H is now pulled back towards the middle a little bit. So this one, one of the reasons it's a little better is that it emphasizes these kind of, these vertices that are connected by just one edge a little bit less. It kind of pulls them back into the fold. And it does a little bit better of trying to ensure that my cuts are balanced. Okay? The differences are kind of subtle and small, but if you're doing this, I'd recommend using the normalized Laplacian instead. Okay, it's not that much harder to use once you start doing the matrix algebra anyways. And it works a little bit better, but again, I would do the same thing. I would draw it on the 0, and that would define my cut. It's the same first cut as before. Okay, and then I would run it recursively where I'd recompute the Laplacian on the normalized Laplacian on each subgraph and repeat. I just do divide and conquer, and I build a hierarchy the same way I did before. Okay, so I won't dwell on that too much. Okay, let's see what else to say. Okay, I wanted to say, so that's basically the algorithm. There's a lot of new ideas in here, right? There's this whole idea of doing this on graphs, creating clusters over the nodes of the graph instead of on some data points and so forth, instead of using a distance. But this is kind of a common formulation. Yeah.
So if your graph is already composed of many connected components, and they're already kind of already clusters, I'm assuming it's not really useful to run this?
Well, you would first split them into the different connected components, and then you may decide there's still too many or too few clusters I want to split further, and then you'd run it on each of the subgraphs. Yeah. If you weren't sure, maybe you just were given this adjacency matrix. If you look at if the second eigenvector is 0, or the second eigenvalue is 0, we know that you have two disconnected components, and that will actually tell you that, right? If you look at the eigenvector, then we'll have some negative, some positive, and it'll give you your answer. I think that's the case. They might be all negative or they might be all positive. You'd have to check, but it will tell you if the eigenvalue is 0, it means you have disconnected components, and then you can go and find them just by doing a breadth first search to find everything connected, or like a union find algorithm, something like that. Okay, so I want to say one more thing about this. So if you do have a point set, I want to use this to do a top-down clustering on a point set with a distance function defined. It turns out the distance function is not quite the right thing to do. Okay, that's not quite the right thing to do, but instead what I want to do, I want to create an affinity matrix instead of the adjacency matrix. Okay, the affinity matrix is going to be A, just like the adjacency matrix. I'm going to set the diagonals, these diagonals to be 0 still. And then entry Aij is just going to be the similarity between Vi and Vj. So if I have a well-defined similarity function, I can just plug this in here, and then I can run the same algorithm as before with this affinity matrix. Okay, so the diagonals would otherwise be 1, which would be kind of not telling you anything. Set those to 0, and then you can define the degree matrix by just adding up the rows. And if it's symmetric, the rows and the columns add to the same thing, and so forth. And then I can just run the same algorithm as before. So if I have a point set, I can run this as well as long as I have a similarity defined. All right, so this is all we really needed to cover today. I think I might wrap it up quickly. I want to mention that the homework 3 will be posted soon, hopefully by Wednesday. And it's going to be on clustering, and it's going to ask you to look at mainly the hierarchical and the assignment-based clustering. There'll be a question on the k-means clustering, which we didn't really talk about algorithms for. So let me just mention that you can run something similar to Lloyd's algorithm, but you need to solve something instead of the average, which minimizes the sum of the distances. Okay, so there's a similar algorithm there you can run. And you know, you can do other things in place of the k-median algorithm. But I'll ask you to solve something for the k-median objective. And I don't want you to run a built-in k-median algorithm like k-medioids, for instance, is built into MATLAB, but that's a little different. Okay, so I'm going to ask you to run the k-medians algorithm on a data set, and that's going to be a little bit tricky. If you give something that makes sense, you'll get most of the points. If you give, but the person who gets the best score in class will get a few more points, something like that. Okay, so you know, if you might lose a couple points if you're not the top person, but it will be like you'll get like almost all the points. So if you do something at all reasonable for that question. But any kind of general, just kind of high-level questions of the k-median algorithm, or an algorithm for a k-median problem, as long as, because this is our last lecture on clustering. No? Okay. So you can run something like Lloyd's, and that's I think that'll be enough to get you started on there. And that and the rest we talked about in class on Wednesday should be enough to figure out something that will get you something like all but 1 or 2 of the points. Okay, so I'm going to end class a little bit early today, and good luck finishing the homework due Wednesday.